Welcome, everyone. Today, we are exploring a critical component of secure architectural design, building trust and distributed systems. Our session, titled Modern Microservice Trust, a Blueprint for PASETO and Rust, provides a guided decision framework for constructing a robust and secure token authority. We will examine why this combination is increasingly favored for modern environments and how you can implement these principles to ensure high-integrity communication across your services. Today, we are looking at the evolution of secure tokens and why we need to move beyond the inherent flaws of JSON Web Tokens, or JWTs. The traditional JWT approach suffers from a significant algorithm confusion risk. This is because the token itself declares which cryptographic algorithm should be used for its own validation, a design choice that has led to numerous real-world security vulnerabilities. Furthermore, JWTs are burdened by an ambiguous KID header and the operational complexity of having to support and check multiple algorithms simultaneously. In contrast, the modern blueprint provided by PASETO solves these issues by design. With PASETO, there is no algorithm confusion because the protocol version determines the cryptography used, rather than the token itself. This architectural shift eliminates an entire class of security problems. PASETO also provides strong, modern cryptography by default and offers a significantly simpler, less error-prone validation logic, making it the more robust choice for securing modern applications. In this architectural overview, we examine the role of a central token authority within a service mesh. This central component is responsible for the issuance and verification of PASETO tokens as requests move between microservices. When implementing this pattern, a critical decision involves choosing between local and public token types. Local tokens utilize symmetric encryption, which offers high speed and small overhead, but requires the complex task of securely distributing shared keys to every service. Conversely, public tokens employ asymmetric encryption, making them inherently better suited for distributed environments. With public tokens, individual services only need the public key to verify a token's authenticity, completely eliminating the need for shared secrets. Consequently, most microservice ecosystems prefer public tokens for their enhanced security posture and simplified key management in complex, distributed landscapes. The first decision we face in building a security-critical service, such as a token authority, is choosing the right programming language. This is not merely a matter of developer preference, it is a fundamental architectural decision. The language we select will have a profound impact on the security, performance, and long-term correctness of the entire system. We evaluate potential languages across 4 critical dimensions. First is crypto library maturity. For a token authority, we cannot compromise on the quality and audit history of the cryptographic primitives we employ. Second, we look at the concurrency model and overall performance. The language must efficiently handle high-throughput requests without introducing concurrency bugs that could lead to security vulnerabilities. Third, we consider the deployment footprint and operations. A smaller, more predictable runtime footprint reduces the attack surface and simplifies operational overhead in production environments. Finally, we assess the ergonomics for writing secure code. The language should provide robust type systems and memory safety guarantees that naturally guide developers towards secure implementations and away from common pitfalls. By weighing these factors carefully, we ensure a solid foundation for our security infrastructure. This language matrix provides a strategic comparison between Rust, Go, and Zig, highlighting their specific strengths and ideal use cases. Rust stands out for projects requiring maximum security and correctness, leveraging its mature cryptographic ecosystem, memory safety guarantees, and zero-cost abstractions. Go is optimized for operational simplicity and rapid delivery, offering straightforward concurrency and deployment alongside a reliable cryptographic library. Zig provides extreme control and minimalism for bare metal performance with very small binaries, though its cryptographic ecosystem is still developing. For the specific implementation of a token authority API, Rust and Go are currently the most viable candidates. While Zig is a compelling technology for low-level systems, it is not yet the ideal choice for production-grade cryptography. Let's take a deep dive into security and performance, specifically comparing how Rust and Go handle cryptographic maturity and concurrency. In terms of the crypto ecosystem, Rust represents the gold standard for this use case. The PASETO crate is highly mature and has undergone rigorous audits. Furthermore, the Rust compiler enforces memory safety, providing a critical layer of defense for cryptographic implementations. While Go is a solid choice and features an excellent standard crypto library, third-party PASETO libraries vary significantly in quality, requiring more careful selection. When we examine concurrency and throughput, Rust delivers extremely high performance through the Tokyo runtime. One of its primary advantages is the absence of garbage collection, leading to zero GC pauses and highly predictable latency at scale. Go offers effortless concurrency via Go routines, but the existence of garbage collection introduces small pauses. As shown in the latency chart, while these pauses are tiny, they make Go's performance less predictable than Rust's under heavy load. Rust is the strongest match for a service where correctness and security are non-negotiable. First, it provides unmatched security guarantees. Its memory safety and strong type system prevent entire classes of bugs common in security-critical code. Second, Rust offers access to gold standard crypto. This includes the most mature, audited, and performant cryptographic libraries, including the best PASETO support available. Finally, the language delivers predictable high performance. Zero-cost abstractions and the absence of a garbage collector mean consistent low-latency performance, an essential requirement for a high-throughput authority service. Our next critical decision involves choosing the right Rust framework for our architecture. The ecosystem currently offers several excellent options, each tailored to different priorities. Axum has become the modern default, known for its modularity and deep integration with the Tower ecosystem. Actix Web continues to be the performance beast, offering unmatched speed and maturity for high-load applications. Warp provides a unique functional filter-based approach that emphasizes strict type safety. For teams prioritizing developer experience, Rocket offers an ergonomic, batteries-included environment. Lastly, Poem provides an Axum-like API with first-class support for open API specifications. When selecting a framework for a token authority, we must prioritize middleware composability, type safety, and seamless integration with a modern service mesh. These requirements will guide us in determining which of these powerful tools best aligns with our security and infrastructure goals. Axum is our recommended choice because its focus on composability and clear separation of concerns makes it the ideal foundation for a security-critical service. First, the framework is highly composable and predictable. Because it is built on the Tower middleware stack, it allows us to layer critical functionality such as authentication, rate limiting, and tracing in a consistent and predictable manner. Second, Axum provides clean and secure layers. Its strong, type-driven design encourages a rigorous separation of concerns. This architecture is ideal for isolating and testing our security logic, ensuring that core components remain protected and independent. Finally, Axum is service mesh ready. It plays exceptionally well with modern observability stacks, including tracing and metrics. This compatibility makes it a natural fit for microservice environments, where visibility and monitoring are paramount. The blueprint for a clean project structure within the Token Authority Service focuses on a clear separation of concerns to enhance maintainability. Within the source directory, the routes folder defines the HTTP surface area, serving as the entry point for all external requests. The middleware directory handles pre-processing tasks, while the services folder contains the core business logic, such as PASETO issuance and verification. We include a domain directory to isolate core entities and rules from external dependencies. Finally, the keys folder is specifically designed to handle key rotation, loading, and publishing. This layout is optimized for clarity and testability, keeping the authority service clean and easily manageable as the project grows. This slide illustrates a code as blueprint example, specifically focusing on the implementation of verification middleware using the Axum web framework in Rust. This pattern demonstrates how to secure an application by processing authentication at the middleware layer. First, the middleware extracts the security token from the incoming request headers. This serves as the initial step in identifying the requester. Once the token is retrieved, the code validates its signature and internal claims against a trusted public key. This step ensures that the token is authentic, untampered with, and currently valid. If the validation is successful, the decoded claims are injected into the request's extensions. This is a critical architectural pattern, as it allows all downstream handlers to easily access and utilize the authenticated user data without revalidating the token. Finally, the middleware passes the enriched request to the next handler in the execution chain, seamlessly integrating security into the overall application flow. The complete blueprint for modern microservice trust establishes a specialized architectural stack designed for maximum security and efficiency. At the top of this hierarchy is PASETO, which handles protocol security and modern cryptography. By using PASETO, we implement a secure-by-default approach to token handling, mitigating many of the common vulnerabilities found in older standards. The middle layer focuses on implementation correctness and performance through the use of Rust. Rust provides the memory safety and type-level guarantees necessary to ensure that our security logic is executed precisely and without overhead, meeting the high-performance demands of modern distributed systems. Finally, at the base, Axum provides a robust and composable foundation. As a high-performance web framework, Axum allows us to build scalable microservices that are easy to maintain and evolve. Together, these three pillars provide a secure, predictable, and high-performance foundation for token-based trust within any modern microservice architecture.